This is the rest of chapter 6.4. This is the rest of the logarithmic functions notes. So this will pick up right after where we left off in the notes. So the next part of these notes is looking at the domain of a logarithmic function. So basically the domain of a logarithmic function. So if I have log with base a of x, then the expression x here, the expression that goes into the log function, must be greater than 0. And strictly greater than. It cannot be equal to, greater than or equal to 0. So the domain of a logarithmic function can only be positive numbers excluding 0. So that means just greater than 0. So in this example right here, it says find the domain of the logarithmic function f of x equals log base 7 of x plus 5 over 5 minus x. So the domain of this function it must be x plus 5 over 5 minus x is greater than 0. It must satisfy that inequality. And to solve this inequality, we look at the breakpoints. This is a rational inequality. So remember, with a rational inequality, you have to look at two places where breakpoints occur, right? Where this is equal to 0, so it's where the rational equals 0. So that's where x plus 5 over 5 minus x equals 0, right? So if you cross multiply here, you're going to get what? You're going to get x plus 5 equals 0. And if you do some algebra there, that was a little messy. If you subtract 5 there, you're going to get x equals negative 5. So that right there is a breakpoint. The other breakpoint occurs when the rational is undefined. So this rational is undefined when 5 minus x equals 0, because then we have division by 0, right? If you solve this, well, that's just simply x equals 5. Right? You just add x to both sides. So this right here and this right here, they're the breakpoints of my rational inequality, right? Those are the breakpoints. That's where the inequality changes from positive to negative or vice versa. So to find where this inequality is positive, right, we draw our number line. We put the breakpoints on our number line, negative 5 and 5. and then we test the intervals. So there's 3 intervals to test: this interval, and this interval, right? So pick a value that's less than -5, and then you're going to put it into this inequality. You're going to put it into this rational term right here, right? So let me choose -6. So -6, store that in the x and type in this. So quantity x plus 5 divided by quantity 5 minus x. That gives me a negative number, right? So when x is -6, that means this inequality is, this right here is negative. All right. Now the value between -5 and 5, so I would pick 0 there. So if you put 0 in here, you know, that's going to be 5 over 5, which is just 1, right? You could do it with the calculator. You're going to get 1. That's obviously positive. Okay, and now pick a value that's greater than 5. So x equals 6. 6, store in the x, and then let's type in that inequality again. So this, and I hit enter, and I get -11. That's negative, which means this is negative over here. So to answer the question of when this is strictly greater than 0, that means when this is positive. Right? If this is greater than 0, that means it's positive. So which inequalities are positive? Well, it's going to be this interval right here. So the interval that's positive will be from -5 to 5, right? Because that's the interval that's positive. So that's my domain of the function. It'll be from -5 to 5. And I'm only concerned about it being greater than 0, right? I can't take the log of 0. I can't do that. Log, you know, a logarithmic function has to be positive, right? When you put in a value into your logarithm, it must be a positive value. It cannot be 0 or negative. Like if you do in your calc, so LO, it doesn't matter what the base of the log is. If you take log of 0, you're going to get an error message. You can't do that. It's not part of the domain. If you take log of a negative number, right, that doesn't work either. Only logs of positive numbers work. So I'm not going to include -5 or 5 because that's when this is going to be 0, which I just showed you doesn't work, right here, right? That doesn't work. And when this is undefined, which is at 5. So my domain is going to be between -5 and 5, not including those values. So that's my domain of f of x. If you were to, you know, let's just imagine that this is log of base 10. All right, the base here is irrelevant for the domain. The domain is everything that goes into the function. The base is irrelevant. Let's just imagine that this is log of base 10 because our calculator only deals with base 10. So let me go into y and type in log of quantity x plus 5 divided by quantity 5 minus x. Close that off. Close off the function. All right, now if I go to my table, if you notice here, all these values where x is negative don't work, except between -5 and 5. Right? So as you can see, between -5 and 5 in this table, right, At -5 it doesn't work, right? We don't include -5 in the domain, nor do we include 5 in the domain. All right, 5 isn't included either. But everything between -5 and 5 works. As you can see from the table, we get values. So, and even though this is a base 10 log, it doesn't matter if it's base 10, base 2, base 7. The domain must be a positive value for the logarithmic function. Okay, the next page, page 3. So, logarithmic functions are, they're inverses of their exponential, of the exponential functions. Yeah, I say cousins here because I'm a funny guy, but a log function is the inverse of an exponential function. All right? So, all these properties that you see here are just the opposite of the exponential properties. Okay? So, if you look at the exponential properties for reference, right? So here are the notes for exponential properties. I know it's hard for me to squeeze both of them in the same view, but if you look at these are the properties for exponentials in the previous section's notes. So the domain and range here are going to be flipped for a logarithmic function. All right. So if the domain was all real numbers for an exponential, then that means the range is all real numbers for a logarithm. All right. If the range was all positive real numbers for an exponential, then that means the domain is going to be all positive real numbers for a logarithm. As you can see, they're flipped. So as you can see here, like for an exponential, right, the graph will contain the points, these points. For a logarithm, if you just flip those coordinates, right, you're going to get the points that are on a logarithm. And you can see that right here. Because, that makes sense, right? When we looked at inverse functions, right, to find the inverse function when you're given the original function, when you look at the coordinates of those, you're just flipping the coordinates, right? And I already told you logarithms are inverses of exponentials. So, one way you could get the graph of a logarithmic function is by looking at these points that contain a logarithmic function, or you could just look at the inverse. You could just, graph the inverse of the function. Remember how the inverse function is symmetric to the line y equals x? You could look at the exponential function, which does something like that, and if you reflect that about the line y equals x, you're going to get a logarithm. We looked at that when we looked at the relationship between inverse functions and their original functions. All right, so if we want to graph this is y equals log base 3 of x. If we want to graph that function, so this is the x-axis, there's the y-axis. So that's going to contain the points 1, 0. So that's going to be right here, 1, 0. The point 8, 1. So the base here is base 3, so it's going to be 3, 1. And the point 1 over a, which here will be a third, comma, -1. So that's a third is roughly somewhere here, and then -1, so it'll be roughly right about there. So if you go from that right there, then a logarithmic function has this kind of that kind of property to it. It has that kind of structure to it. And if you were, you could kind of see how, this is log base 3 of x. Here's the inverse of that function, 3 to the x power, right? You can see how this graph is symmetric to this graph if I drew the line y equals x, right? This is the line y equals x. Remember when we talked about inverse functions? To graph the inverse, you just take this graph and you reflect it about the line y equals x, and you're going to get the inverse function, right? This is f of x equals 3 to the x. This is f of x, or well, y equals log base 3 of x. So you can kind of see how they're related, right? You could go from one to the other or vice versa by just reflecting it like that. So yeah, this is the graph of a logarithmic function. Notice how there's a vertical asymptote at 0. Just like here with an exponential, there was a horizontal asymptote at y equals 0. Here there's a vertical asymptote at x equals 0. You can see how a logarithm only takes positive values for x. It's strictly on the right side of x. And I don't get any negative values for it. And the logarithm could be positive or it could be negative. The result of the logarithm could be positive or negative. But the logarithm itself only takes in positive values of x. So, that's a basic graph of a logarithm right there. Well, just like, so let me refer back to the exponential notes here. So just like a to the x was a specific base for an exponential function, right? We had base e to the x, right? We had base e to the x where e was a specific number, e to the x power. That was a specific exponential function. Well, similarly, by extension, what we could say is, we mentioned how, we mentioned this number e as a specific base, which occurs a lot in real-world applications, right? So, since we do have an exponential function, which we know as f of x equals e to the x, well, then this has a corresponding logarithmic function as well, right? So, if I want to, if I have base a, right, and this is base e, right, base a functions, base e functions, so exponential and logarithmic. So if I have a base a, my exponential function is f of x equals a to the x power. Its corresponding logarithmic function is log base a of x. If my base is e, we know that f of x is equal to e to the x power. That's a specific base of e when, that shows up a lot. Well, what I'm talking about here is, in this definition, since this exists, this has its own unique logarithmic function. All right? Base a has its own unique logarithmic function, and f of x has its own unique logarithmic function. if my log is base e of x, we don't write it this way. We call it the natural log, ln of x. And that's what I'm talking about right here. So if I have log base e of x, we write ln of x in place of log base e of x. We don't write it this way. This is redundant. We just say this is called the natural logarithm. All right? And regardless if you're working with base a logarithms or base e natural logarithms, the properties for them remain the same. Okay? They're exactly identical. They're no different. So, depending on what base you're working with, you're going to have a specific exponential function and an associated logarithmic function. It's either going to be this kind of logarithm, which is a base a log function, or you're going to have a natural logarithmic function. We just call this the natural logarithm. So whenever I say natural logarithm, we're talking about base e exponential functions, really, as its inverse. When I say log, that means I have a specific base. That could be base 2, base 3, base 5. Usually it's implied to be base 10, etc. So, again, when we talk about logarithmic functions, we are usually referring to ln of x, just like with e to the x with exponential functions. That basically, all I'm saying here is that if I'm working with e to the x, a logarithm is a specific type of logarithm, a natural logarithm. We write this as this. That's all I'm saying. So when it comes to graphing a natural logarithm, it's the same process as graphing a, the same properties apply. On the previous page, it's the same process as this for a log logarithm. Whether it's log or ln, the same properties apply. The same kind of graph applies. These points apply. Everything applies. So I'm graphing natural log of x minus 2. Right? So if this is my x-axis and this is my y-axis, so the first thing I want to do is I want to start with, I'm using the technique of transformations, right? I'm starting with the most basic form of this function, which is ln of x. That's the natural logarithm. And this has the points. This has the points 1, 0, a, 1. So the base, since I'm working with natural logarithm, the base here is e, 1. And the point 1 over a, which the base here is e because it's natural logarithm. So it'll be 1 over e, negative 1. So, if you wanted to approximate what those values are, just type e into your calculator. So second, e to the x is right above ln. That's why e to the x and ln are, they're really close on the calculator because they are related. They're inverses of each other. Just like log and base 10 exponentials are inverses of each other. That's why they're really, that's why they share the same button essentially. So e to the first power, we already know that's 2.72, right? So this is the ordered pair 2.72, 1. And this right here is the ordered pair, so 1 over e to the first. Oop, not 0. First. That gives you 0.367, so that's a little fraction, right? But it has the same, it has the same property. So 1, 0. It's roughly right there. E comma 1, so that's 2.72 comma 1. So 2.72 comma 1 is right about there. And 1 over e comma negative 1 is right about there. So you can see how the property, you know, the structure of this graph kind of looks the same, right? It looks like a logarithm, right? And then it's going to hover out like this. Now that's the graph of ln of x, roughly. But I want to graph the natural log of x minus 2. So to go from here to f of x equals ln of x minus 2 by using the techniques of shifting and compressing and whatnot. You know, if I'm subtracting 2 from x, that means I'm shifting this graph to the right 2 units. That's what it means. I'm taking this graph and I'm picking it up and moving it to the right 2 units. So if this is 1 comma 0, then, you know, this is a rough sketch, obviously, but so right about there is roughly, you know, if I'm shifting this 2 units, right? So this will be roughly, if I shift that 2 units to the right, then that'll be the order pair 3 comma 0. This will be the order pair over here. So I'm shifting the x coordinate to the right 3, and I'm shifting the whole thing to the right 2 units. So that'll be e plus 2 comma 1. And then I shift this to the right 2 units. So that'll be roughly right there. That'll be 1 over e plus 2 comma negative 1. So this graph right here is roughly the graph of f of x equals the natural log of x minus 2. Just to get you an idea of, you know, natural logarithms and how they're, you know, the graph of a natural logarithm is the same as the graph of a log function. But to go from one to the other using the transformations technique that we learned in chapter 3, that's essentially how you would do it. Okay? So I mentioned this already, but I mentioned how your calculator only deals with base 10, right? If the base of a logarithmic function is not expressed, so if you don't see a subscript on your logarithm like you do here, right? You don't see a subscript, then it's understood to be base 10. So we don't write log base 10 of x. We don't write that. That's redundant. We just write log of x. And like I said, your TI calculator treats logs as base 10. If you want to evaluate logs at other bases of a, you'll need the change of base formula for logs. And we'll look at that in the next section. But basically, if you want to evaluate your logarithm at other values besides base 10, like if you have base 7, base 3, base 2, base 5, whatever, you have to use the change of base formula. So whenever you, and if you look at your calculator, right, LOG, right above the LOG button, you see 10 to the x power. That the calculator is literally telling you that my logarithm is base 10. So when you type in log, you're really working with base 10 here. This is 10 to some power gives you that result. Okay. So just be aware of that. If you see LOG of x, that means this is base 10. Otherwise, if you see LOG with an A there, that means it's base A. That's all I'm saying. And we choose, we choose base 10 because if you think about it, 10 to the first power, 10 squared, 10 cubed, 10 to the fourth, you could do those computations really quickly because 10 to a power is just adding on a bunch of zeros. And that's easy to do as opposed to like 5 to the base 5 or base 7. You could do powers of 10 relatively quickly. That's why we choose to work with it. Okay, now when it comes to solving logarithmic equations of, some logarithmic equations can be solved by converting the log function to an exponential function, or vice versa. More sophisticated versions will require properties of exponents in logarithms, which we'll look at in the next section. But when it comes to solving some types of logarithms, you could just rewrite the logarithm as an exponential. Okay. So if I rewrite this as an exponential function, so my base 5, this is log base 5 of 3x minus 4 equals 3, right? So I have base 5, right? I start at the base, then I go over here. That's the exponent. So this is 5 cubed equals the result. The result of this exponent is going to be the expression that goes in the logarithm, which is 3x minus 4. Just by rewriting this logarithm like this, now I could solve this equation. This is a simple equation. 5 cubed is 125 equals 3x minus 4. I could add 4 to both sides. So I have 1. Let me come over here. So I have, they cancel out. So I have 3x equals 129 divided by 3, and x equals what? So 129 divided by 3 gives you 43. Now, since we can't technically check this in our calculator yet, because, like I've said already, your calculator only deals with base 10 logarithms. But we'll be able to check these in our calculator in the next section. We've got to use the change of base formula. So my solution set here is 43. And that is a horrible looking number 3. There we go. you know, once you put 43 in here, you know, you're going to get 5 cubed equals 125, which is obviously true. Okay. Now in this one, this is an exponential, so I'm going to rewrite this as a logarithm. So my base here is E, right? So that means I have a natural logarithm, right? This means I have a natural log, ln. Now the result, right? The result of this exponent, right, is what goes in. That's what goes inside of the logarithm, right? So the result of this exponent, which is 7, goes inside ln. And that's going to equal the exponent, which is 3x. So by rewriting this as a logarithm, that's what it would look like. You know this because of the relationship between logarithms and exponentials, how you go from one to the other, right? So natural log of 7, this is just a number. Here's the ln function right there. ln of 7, that's just a number. We don't write out, we could approximate the number if we wanted to, but we just keep it in exact form. ln of 7. So this is a number equals 3x. So to get the x by itself, you divide both sides by 3. Threes cancel, and then you get x equals natural log of 7 over 3. And that right there is the exact answer. We could approximate that. Natural log of 7 divided by 3 is approximately 0.648 blah blah blah. So I could approximate that. All right? This is approximately 0.648, so 0.649 if I wanted to do that. But the solution set, we use exact values, which is natural log of 7 over 3. So, a lot of these logarithmic equations or exponential equations, there's a chunk of them that could be, solved by just rewriting a logarithm as an exponential or an exponential as a logarithm and go from there. But sometimes you can't do that. Well, for other kinds of logarithm and exponential equations, you can't do that. So to solve those kinds of equations requires looking at properties of logarithms, which is the topic in 6.5. Okay, so this section was to give you exposure to the relationship between a logarithm and an exponent. In the next section, we're going to look at properties of logarithms and operations involving logarithms, what you can do with logarithms, stuff like that. So that's the end of this video.